Alright, welcome back to the SciMax channel. Today we'll see version 3 of my semantic completing read idea. So the gist of this idea is we have a lot of candidates, say words or sentences that we want to use in a completion in Emacs. That means I want to easily get all of these candidates and be able to narrow down to the one I want. And previously I showed you some ideas about how to do this semantically, where we can take a word like fruit, generate a numeric vector, and compare this vector to all of the vectors of these words to see which ones are semantically close. This is a common task in large language modeling now, and we use it in the semantic completing read for Emacs. Now, I made a couple of videos before. In version 1, I used a Python command line program that I wrote. You would pre-compute all the embeddings and then pass a query to it as a command line argument, and it would pass back the candidates for you to look at. It turned out it was really slow. It did work, but it was slow and it wasn't that convenient to pass candidates to. And it only worked for some BibTeX entries that I knew I could pre-calculate those candidates. But it took like 2 or 3 seconds to run that command line program, and that was just too slow for practical use. In version 2, I solved that slow startup cost by making a Flask app that basically runs a little Python server, and you use a REST API with HTTP requests, and you can get the things that you want there. And that also worked pretty well. You did have to run the server and do some port management and distribute that server app. I did that through some strings, and I didn't love it, so I didn't release that version, but you can see the previous video here. In this one, I took a totally different approach. Instead of running a Flask app, I took advantage of the idea that with Jupyter Emacs, we can start a Jupyter kernel, and then I can use Emacs to communicate with the kernel and get the results back. And that works out well enough that I've gone ahead and put in a semantic completing read. You can find a link to that library in SciMax in the video description. And today I'm just going to show you, kind of how it works. In lots of ways, it's the same as I showed you before, but we'll go through it again. So this is something that you might do with completing read. Maybe I'll do the same thing that I did once before. Let's just copy this and show you what I would do in the past. If I wanted to use this for completion, we might use something like Ivy or completing read, and in the simplest form here we just say Ivy read or completing read, give it a query thing, and then we have a list of candidates. So here I have a bunch of sentences. Here's one, a multi-line sentence, and another one and another one. So here, if I run this at the bottom, you can see I get all of these different ones. And let's say this is really long and you don't remember it, but you're looking for a sentence and you remember something like fast wolf. You can see if I type in fast, you don't see anything at all. Now, obviously, fast wolf should be close to quick brown fox or something like that. So that's not very helpful in normal completing read. Now, what I did here was wrote a function called scrread for semantic completing read, and we give it the same list of sentences. We have to give it a name here. This would be like the caller in Ivy. But now when I run this, if I type in fast wolf, eventually it narrows down, and you see that the most likely candidate is the quick brown fox. And we can do other things too, like maybe canine. Canine also makes that come up. Or if I put in collection, then the one that is closest is this thing that has a list. That's kind of like a collection. And so that's pretty nice. And you can give it an action. Here I made it make a message box that doesn't show in the video because it's not in the window that I'm sharing, but this is just an option that you can give completing read. All right, I showed you this one before. Let's say we have all of these words and we want to choose them. I'm going to use initial input of fruit, and that's going to put all of the fruits up at the very top. All right, if I delete this and say pet, then we get dog and cat, or animal will show all of the animals. We can get a tree, and you see these ones here. So again, we can use this for sort of semantic grouping and completion and order them in ways that are ranked by similarity. This one was inspired by a comment in the second video, which is finding related commands. So if we look at this function here, this gives me, I use IV and counsel, this will give me a list of all the commands. And if I run this, it takes a little while to load all of these. I've run this before. There's about 12,000 things in here, and it is loading them in batches. It does cache these, so there's only a one-time cost in each session. It's not a it's a semi-permanent cache that makes it a lot faster to run. But one of the things that I had to do when I worked this out was I tried to limit the embedding, uploading the candidates to like 100 per batch, so that we don't run into any timeouts in Jupyter. I don't know how critical that is. It's a settable property, and I have it set to 100, so that's why there are 127 batches that get run. But when this finishes, we have an initial input of conceal. So this is going to rank all of the commands by similarity to the word conceal. And that's going to show us things like hide and other things that are related to it. Okay, so we see, hide, reveal, lots of hide options like that. So it's pretty helpful. Let's run it a second time. It should be quite a lot faster because now that result is cached, and it doesn't have to look it up or recalculate it every time. So I think that's kind of interesting. If you don't know what the function is exactly, you can use this for it. There is an interesting thing here I wrote in for debugging. So if we go to this buffer that is created, then you can see some things in here of all the code that is sent to the kernel that might be helpful in trying to debug it. And down here is an actual kernel, so we can type in some commands if you know what these are, and you see there's 12,606 candidates. And let's look at the first few. Let's say 10. So this is a regular Python REPL. All right, so let me show you a little bit behind the scenes how this works. So we have down here the Completingread function. So it's a common Lisp def-un. We give it a list of candidates. We give it a name and any IV options. This will initialize it. We'll get to that one in a moment. Let's just do it now. Initialization here just creates the Semantic-completing-read buffer, and then down here we create a Jupyter REPL in Python, and it associates it with that buffer. Then the startup sends some Python commands. So here we do lots of these Jupyter eval inside the buffer. We import some libraries, item getter, this is the vector database, this is the transformer we use. Down here we have some dictionaries to store all of those in for different completers. We have some function here to convert things to Lisp. Here is a function for getting and embedding. You give it a bunch of strings and a model name, and it will encode those embeddings and return them. And then here is how our search works. We have some embedding of a string that we're querying. We do an index search here with that embedding, and we get these matches, and we just return a Lispified string because we read it in later. All right, so that's the startup. After that, we have a function here to set the model. So for each time you run this, that name is a caller. We're going to create a model here. So if the model has already been made, we look it up. Otherwise, we create it and encode a test string so we know what dimension it is and create the index for it. There. Okay, then we load those candidates. This also is just some Lisp code. This will read in that we have, if the candidates change, we don't change anything there. And then here we reset the index and store the candidates here. And eventually we loop over a bunch of batches where we update the candidates, get our embeddings, and add it to the index. All right, and then all the magic actually happens here. So we run ivy-read on this search function. And the search function is run every time you update the mini buffer in Ivy. So every time you change the candidate, it will either show you all the candidates at the beginning, or it will run a search right here and give you the new candidates and update them as you typed. All right, that's basically it. And there's only a couple limitations. It's still kind of slow. If you have 12,000 large strings, it's going to take a minute or something to run through the embeddings. At that point, you probably want some more dedicated solution. You can still find a way to pre-calculate them perhaps and import that into a Python library, or you'll have to get quite a bit more clever at making this work before then. Like maybe you can store everything in a database with pre-computed embeddings and just load the candidates and embeddings at the same time. That could be something that's interesting. Anyway, the code is available. You should give it a try if you find this kind of thing interesting, and it's certainly not stable. I think there's still some corners and edges to polish and figure out how convenient it is for the cache mechanism, for example. I'm also not positive that the cache mechanism I use for disk persistence is the best one. It's a little bit challenging sometimes. If you change the model, you run into cache invalidation challenges. But I think it's an interesting idea, and look forward to working with it in the future. So thanks for listening, and this is version 3 of the Semantic Completing Read.